All right, what's up, everybody? Welcome back. And we're getting back to engineering dynamics here, and we're going to do a problem here on with kinetics of particles. And this example is going to be using kinetics with rectangular or Cartesian coordinates, or just the standard XY coordinate system in 2D here. And what we're given is this problem here is that we have boxes that are transported by a conveyor belt or some way to this ramp here from A to B, and these boxes slide from A to B for a length of 6 meters. And what we know is that the coefficient of kinetic friction when the boxes are on this ramp is mu k is equal to 0.4. The angle of this ramp is 15 degrees. And then here, the velocity when it leaves a ramp is 2 meters per second. And you can envision maybe a projectile motion problem here where it falls into a bin or something, in some sort of uh, manufacturing plant or some industrial plant or something, right? But what we want to know is what is this velocity here at the top? So essentially, like what's the conveyor belt delivering these boxes at? And so we want to find the velocity at A. I want you to also note that the mass of these particles is unknown. Okay, and the way we're going to go about this problem is, as you can imagine, you're going to draw a free body diagram of this right here. Okay, and it's going to be really important that you draw the free body diagram draw a free body diagram and establish that coordinate system. Okay, so plus, and we want to pay particular attention to the coordinate system that we use, okay, and how we define positive. And then two, we're going to apply Newton's second law. Okay, Newton's second law here, or F equals ma. And this right here is we want to make sure that we have essentially our free body diagram parallels, this Newton's second law. That's the way we want to do it. And then we're going to solve it, and then we're going to probably use some kinematics here. Uh, we're going to, well, here, let's go back a little bit. We're going to use Newton's second law really to get acceleration of the particles. Acceleration. And once we have acceleration, what we want to do is we're going to apply kinematics to get the velocity. Okay, so let's see how that's done. Okay, let's go for it. So the first thing that we want to do is let's draw a free body diagram of the box somewhere along this path here. So somewhere along this path here. So maybe I'll draw the box over here. So if I look at that box right here at that instant of time, so here one FBD or schematic. I like to use schematic here. Schematic of my particle and the forces that it experiences here. So I have this 15-degree incline. I have a box here like this right here. And let's make sure it's a little bit cleaner drawing. Let's use my straight edge. Yes, okay, right here. And this angle right here, this angle of the incline is 15 degrees. What I want to, what the first thing I want to do is I know that I'm going to need an external force diagram, okay? An external force diagram, and I want and an inertial diagram. So I want this exact same drawing here. Fortunately, I have like a computer kind of deal right here, and I can just bam paste it onto here and move it into place. Nice, right there. And I don't need this stuff right here. This on this side of the equation will be my inertial diagram. This I'm going to call the inertial. Oops, inertial diagram. This will be my inertial diagram here. And and what we want to do, really, the first thing when we draw this FBD is establish what our coordinate system will be. And because, just for convenience sake, because I know my particles are moving down this path, I'm just going to choose going down the path as my plus x direction, and my plus y will be upwards, plus y here. Bam, plus y. Okay, like this. Plus y will be that direction here. And then I want to do the same thing here. I want to say here. And really, it's not really that we're drawing it on the particle. It's more like we're establishing it over here. If this is my origin as plus x, and plus y like this right here. And we're just putting it here, these dotted lines, just so that we can draw the forces better and come up with angles and things. Okay, and the same thing here. We want to keep the same x and same y, and what we'll have is this, this plus x direction and this plus y direction will be consistent on the particle. And so now I have here, let's start with the external forces. I have a normal force on the block. Okay, normal force on the, I'll call it block. Okay, end block here. And then I have the force of friction, F sub F. I have the weight of this block. So I'm going to go this straight down, W like that. And I don't think there's any other external forces. I think that's about it. Okay, I think that's it. And then here, the inertial side, I just want to draw my inertial terms in the same direction, or draw them in my positive sense. I don't know what the resultants of this is going to be, but I want I'm just going to draw it in the positive. So I'm always going to draw my MAX this way and MAY this way right here. And some of you are probably saying, why did you draw MAY? Why did you draw MAY? Well, I just drew it just to be complete. But the reality is that this block never moves in the y direction, so this acceleration in the y is actually 0. Okay, that's going to help us out a little bit later. All right, so this is our external force diagram and our inertial force diagram. We got to work out some geometry, and what's something you'll notice that this is 15 degrees, and just by, parallel lines and all that other stuff here, this is also 15 degrees. And what we're going to do is break this up. This weight is going to be broken up into, let me, 15 degrees right there. This weight here is going to be broken up into the a y component and an x component. Okay, so hopefully you can see that coming, but that's what we're going to be doing right here. And so now the next part here, once you have a good external force diagram and a good inertial diagram, then it's all about applying Newton's second law, or the equation of motion. Okay, apply F equals ma. Okay, apply F equals ma right here. And so here, what we're going to do is, because this F equals ma is a vector equation, we're going to break it up into components and look at one dimension at a time. So in the x direction, sum of the force in the x equals max. My positive x is down, it's downwards this way. And so my equation here, by doing that, would be, I would have plus wx minus f of f is equal to, so here's my external force side, is equal to max. And just by pure geometry, we know that wx right here, if I could have, normally I would just write this as w sine of theta minus f of f equals max, like that. I would just run it there. I wouldn't even mess around with this wx business right here. Okay, then I want to do the sum of the forces in the y direction as well. Sum of the forces in the y equal to, here, here's my positive y orientation, and this would be may right here. So I would have, in the y direction, I'd have minus wy plus nb, n block, is equal to may, which we already said is 0, because our block never moves in the y directions here. And that just tells us that this w, and then again, I wouldn't normally write this wy, but this would be minus w cosine of theta, where theta is 15 degrees, plus n block is equal to 0. Okay, so that's good news. So what you see here is, you'll see that this w really is this unknown. This is mg sine theta minus, and if you recall the definition of the force of friction, F of F right here, is kinetic. Mu k times the normal force right here. Okay, so the coefficient times the normal force on the block right there. And this is this other equation to help us get rid of an unknown. So this right here is this mu k times n block here is equal to max. And so what we have in this equation here is, we have 1, 2, and 3 unknowns. So here I'll circle this one. I'll put a block around this one because it's a block. And then here I'll have, oh, that makes it look like, well, actually the mass is also unknown, but here, bam, I'll do this right here, and then I gotta circle the mass there. So really I have one, two, three unknowns, and really only two equations left. So let's proceed with the way it is. I'm sure some of you can already see what's going to happen here. So I have this minus mg cosine theta plus n block equal to 0. And here, n block is equal to mg cosine of theta right here. And so now I'm going to substitute this into here. I'm going to combine those two equations right here. And so that'll just be mg sine theta minus mu k mg cosine theta is equal to max. And what I have here, look at that, look at how that works out. It's that these masses all cancel out right here. And that actually happens a lot in dynamics problems, especially when the mass isn't given. The masses usually will cancel out. And and here, what this will become is, quite simply, there's only one unknown left here. It's this acceleration here, and what this gives us is that I have here g times the sine of theta minus mu k cosine of theta is equal to the acceleration in the x direction. And this acceleration, and if I now plug and chug some numbers, this will be 9.81 meters per second squared times the sine of 15 degrees minus 0.4 times the cosine of 15 degrees. And let me make that bracket is equal to the acceleration in the x. This acceleration in the x comes out to AX is minus 1.25 meters per second squared. And what this negative means is that the acceleration vector, or this inertial term, the acceleration vector is actually pointing the other way. So this particle going uh, part from point A to point B is actually decelerating due to friction, right? So here, so with that acceleration is a deceleration, okay? So this AX is actually, if I want to write this properly in vector form, is 1.25 meters per second squared this direction at 15 degrees. So an acceleration is provided uh, as long as you give a magnitude and a direction. That's your correct answer for acceleration. But that's not where we want to be. We also want to determine what the now we want to use our kinematics and determine what the velocity of this thing is when it reaches, or what it was at point A. Okay, and so here, our last part of this is to use our kinematic relationships, 2, 3, kinematics. And here I just have plain 1D motion. And because the only thing that's really acting, the only force that's contributing to acceleration, if you will, is gravity itself, I know that the acceleration is constant. Okay, so this is actually a case of constant acceleration. Okay, I don't have any sort of varying force to vary the acceleration. I'll have a constant force, weight, basically pushing down or causing it to move downwards. And so here, I have this constant acceleration case here. And that means, and what I also have in this case is I have the distance that this thing travels. The particle travels a distance of 6 meters. 6 meters right here. And I also have I have the final velocity VB, which is here of 2 meters per second squared right here. I'm sorry, 2 meters per second, this final velocity of 2 meters per second. So if you look through your constant acceleration equations, and I'm sure I have a derivation of this somewhere, but here, this you would use as VB squared minus VA squared is equal to 2 times the acceleration in the x times the change in position right here, okay? And this is just from really, coming up with a constant acceleration. It's, you had this, if you, I don't know if you remember this, but you had S, final is equal to S0 plus V0t plus 1 half AT squared. and then you had a velocity equation. Velocity final is equal to v0 plus at. If you combine these two equations and get rid of time, you get this. Okay, that's what you get. And delta S right here, delta S is just SF, S final minus S0. Okay, so that's what's going to happen here. And that's where this comes from, or A, acceleration in one dimension, or X in this case right here. Now, if we're going to keep this positive motion downwards here, okay, and our acceleration is in the opposite. So in this case here, when we apply this right here, this VB squared, this is going to be 2 meters per second quantity squared minus VA squared, the value we're looking for, is equal to 2 times negative 1.25 meters per second squared. So this negative is really important because we're decelerating in that direction. And then the distance traveled is 6 meters. And when you go through and you plug and chug for VA, or you solve for VA here, what you'll get is that at A, at the part at point A, the velocity was 4.36 meters per second. Bam. Okay. Bam, right there. So the velocity at A was 4.36 meters per second. If I want to give a really a more precise result to that velocity would be in vector form 4.36 meters per second, a magnitude in the downwards like this at 15 degrees. So with direction and again magnitude. Yes. All right. So hopefully that was enjoyable. Okay. Um, Another thing you want to think about is later on, this problem is actually easier to solve using principle of work and energy. So if for those of you who are into it, go for it. Try to solve it with principle of work and energy. And maybe I'll do it the same problem with principle of work and energy so you can have like a comparison, right? Okay. So hopefully you enjoyed that. Let me know if you have anything you want to ask.